Hey guys, so I'm going to go over problem 510 from Taylor today. Let me share my screen. Cool, so chapter 5 is all about harmonic oscillators. I wanted to pick a problem which is related to my mini lecture on why we bother studying harmonic oscillators in the first place that exemplifies how this works out in practice. Namely that you can take a potential, study it near equilibrium, it's going to look like a harmonic oscillator. So problem 510 is as follows for those of you that don't have the textbook. Let's say that you have a system which is subject to a force that looks like this. It's negative F naught times hyperbolic sine of alpha x. So here F naught and alpha are constants. What we want to do is the following. Find the potential that would give you this force, and then approximate the potential for small oscillations. And what we mean by this is for small values of x. And then after doing that approximation, what we should find, and they don't say this in the statement of the problem, is you should find a harmonic oscillator type solution, and therefore we can find the angular frequency of oscillation, which is defined in the textbook. Cool. So how do we go about doing this? For conservative forces, the definition of a force, and this is in multiple dimensions, is the force is equal to the negative gradient of u, which is a function of the different coordinates in your system. This problem is simpler because it's in 1D, and so let's relate this to the one-dimensional version, which is just you have a force, which isn't a vector in this case, and this is just equal to negative d dx of u of x. And here, x is just a scalar coordinate, a single coordinate. You can invert this equation by using fundamental theorem of calculus and find the equation that relates work to forces, which is that here's the multidimensional version. If you do work from one point to another and you go along some trajectory, you take the dot product of the force along that trajectory and you're able to get work out. And again, we only need a one-dimensional version of this, and I just put the multi-dimensional version up for your own reference. In 1D though, this is pretty simple. We go from one point to another in which we are doing work, take the force, and just integrate over those 2 points. Cool. So one thing that I want to point out is that you have freedom in what the first and second point is. However, one of the points should be equal to x, and we should use a dummy variable x prime in defining this. And the reason why is that we want u to be an expression of x, and then otherwise we're just going to have some arbitrary constant which is independent of x that's going to show up. So how do we actually write this? U of x is equal to minus integral from some x naught to x of f of x prime dx prime. It's important that you use the dummy integration variable because the expression just wouldn't make sense if you said instead u of x is equal to negative integral from x naught to x of f of x dx, because x is showing up both in the bounds of integration and also in the variable that you're integrating over. That's a nonsensical expression. So when we do this, I'm going to choose, and this is my choice and my choice alone, x naught is equal to 0. And that's just going to eliminate the constant in this problem for us. So what this means is the following. This is going to be equal to f naught integral from 0 to x of sine h alpha x prime dx prime. And so integral of hyperbolic sine is hyperbolic cosine times 1 over the argument in front of what you're integrating over. So we're integrating over x prime. Argument in front of that is alpha. So we get a 1 over alpha. We get f naught over alpha cosine h alpha x. So that's the potential. Now, what we want to do next is figure out what is the approximation for small oscillations about equilibrium. So the definition of equilibrium for a system is when the derivative of the potential is equal to 0. And so this is going to occur at a point or multiple points. So it's possible that you have multiple equilibria. However, in our case, there's only one equilibrium point. X is equal to 0. So you can check this by setting the derivative equal to 0. The first derivative of u is going to be sine h. And you can just plug into the expression for sine h or Wolfram or whatever you like and see that there's only going to be 1, 0. So if we want to do an expansion around there, we need to do a Taylor series expansion. And so if I wanted to keep every single term in the expansion, it would look like this. Again, this is the equilibrium point that we're expanding about, which is why I plugged in 0. The parentheses n that is a superscript to u is just saying n derivatives of u with respect to x. And then we have an x to the n. Now, there's a couple things to note here. X is small because we are looking at small oscillations, meaning just small deviations from the equilibrium point, which is 0. Because x is small, we're only going to keep the first term that has some power of x that's non-trivial. So we're going to get some constant. So u of x is approximately a constant, which is just the first term in the Taylor series. It's physically irrelevant because when I take a derivative of u to get a force out, the constant vanishes. This term goes away because of the definition of equilibrium, which is that the first derivative of u is 0 plus, then we get 1/2 u double prime. So 2 derivatives of x evaluated at 0 times x squared. This is the first non-trivial term that depends on x. It's the x squared term. And so we're just going to cut the series off there. And we can justify that because we're saying that x is small. So all the other subsequent terms in the series are going to be even smaller than this term when we are only restricting ourselves to small x's. So what that means is that this is approximately f0 over alpha times 1 plus 1/2 alpha squared x squared for the potential that we're interested in. And so this is 1/2 k x squared plus a constant. And that identifies k is equal to alpha f naught. You got everything right. So last piece of this problem is, what is the angular frequency of oscillation? Well, this just has a definition that you can find in the book. It is omega, which is the square root of k over m. We've already solved for k because we've identified that with the appropriate quantity, which would make this look like a harmonic oscillator potential, and that's alpha f naught. So we just get square root of alpha f naught over m. Cool. So that's problem 510. Pretty straightforward. This is more of a warm-up problem to get used to some of the concepts that show up early on in the book. If you guys have any questions, just send me a chat on the Discord channel and I can answer those. So great. See you for the next one.